Okay, people, we are going to go through the energetics review package that I gave out last class or whenever that was. So here we go, starting with number 1. Keep in mind that energy is given by mc delta T, where m is the mass of the thing that's being heated up, c is the heat capacity, there it is there, and delta T is a temperature change in Kelvin or degrees Celsius, which is 5, given from that information right there. So you plug everything in. And keep in mind that this is a non-calculator section for the test normally, so multiply the 2 by the 5, so 10 times 0.9, and that gives you 9. And there's the answer. Okay, moving right along. Number 2 here, the question is just asking to find Q, and the thing to notice is because C is in joules per gram per Kelvin, and because because the temperature increases by T degrees Celsius, that's also the temperature change in degrees Kelvin as well, so that's fine. And the mass is given in grams, so my answer is going to be in joules, which is what it wants. So in other words, the answer is simply A, mc delta T or mct, same thing. Okay, you do not need to add 273 because it's the change in temperature. You do not need to divide by 1,000 because I don't want it in kilojoules. I don't want the mass, the mass is not in kilograms, etc. Okay, well for this one here, the temperature increases by 3.5 degrees, so obviously then it's exothermic. And again, it's exothermic because heat was released, which is why the temperature increased. And that's all the marks for that question. Explain why the solutions were mixed rapidly. Well, this is just like the Hess's law experiment we just finished doing, and that is we want the reaction to happen as soon as possible so that we have less heat loss to the surroundings. In other words, we want the reaction to happen quickly so we can measure the total temperature change. Okay, so we simply want to minimize the amount of heat lost. Next question, which is to calculate the enthalpy change. So again, we want to know what Q is. So mc delta T, and of course it says we can use the approximation that C is the same as that of water, so 4.18. The mass is the mass of the substance that's heating up, which is the 100 milliliters of solution. And assuming it has a density of same density as water, that's going to be 100 grams. So that's going to give me my Q in joules. And then to get delta H, I need to do Q divided by H. Sorry, that's Q divided by N, the moles of the limiting reactant. Since we're dealing with a solution here, moles is equal to the concentration times the volume. Concentration is 0.5, volume is 0.05 liters, which gives us 0.025 moles for each of the substances. And they react with a 1-to-1 ratio, so therefore I have an equal number of moles of each, and therefore the limiting reactant, well, there isn't one, they're mixed in the appropriate amounts. So then I just convert that to kilojoules. So 1.463 kilojoules divided by 0.025 moles, and that gives you your answer. Identify the major source of error in the experimental procedure and explain how it could be minimized. With all of these, it's, well, I can say all, but most of them, it's due to heat loss. Heat is escaping to the surroundings, or it is being absorbed by the calorimeter, where the reaction is happening. So that's the major error. And to get rid of that, you can either insulate the beaker or you can calibrate the calorimeter. In other words, measure how much heat the calorimeter or the reaction vessel, the beaker, whatever it is absorbing. That's another one you could do as well. The experiment was repeated, but with an HCl concentration of 0.51 mole. In other words, we've added more of our acid. The amount of liquid is the same, so the mass doesn't change. The amount of the C doesn't change, and delta T, well, okay, so is that going to change? That's what the question is really asking. Well, keep in mind that Q is right here. Sorry, delta H is right there. It's 58.5 kilojoules per mole. Per mole of what? Per mole of the limiting reactant. So by adding 0.51 molar, that means that the HCl is no longer the limiting reactant. It's the reactant in excess. The other one, the KCl or the KOH or whatever it is, that one is now the limiting reactant, and there's still just 0.025 moles. In other words, the reaction won't change. You're not going to get a different change in temperature because you have everything is still the same. The number of moles, this here, is still the same, and therefore nothing changes. Alrighty. Here's one, a Hess's law type question. Trying to find the value of delta H for the following reactions. So we are going to do some equation manipulation here. Actually, I solved it using an enthalpy cycle diagram. So you can sort of see that the arrows kind of point this way or this way. So both pathways must be the same, which means that there, and just solve for x, and you get 142. Okay, this is one here we could use where we use the equation manipulation. Might be a little bit easier because they give you the heats of formation. So there is a bit of a shortcut, but let's do the long way first. There's the first equation. You'll notice I've written it backwards because CS2, carbon disulfide, appears on the left. So I want to put CS2 on the left as well for my equation, which means I have to take the opposite sign of that because the heat of formation is when you make CS2, but here I'm decomposing it. Same energy change, opposite sign. Let's look at the next one. Oh, oxygen, by the way, is 0, so that's easy. CO2 is written just normally, and then SO2, you'll notice I doubled everything because I want to make 2 SO2s. Okay, let's start canceling everything out on both sides that appear. Like, for example, the C there cancels out, and the 2 S's there cancel out. And that leaves me with CS2 plus 3O2 produces CO2 and 2SO2. So basically I just had to add everything up here, and it's negative 1080. And there's your answer. The shortcut way is that there where you take the delta H to make all the products. In other words, 1 CO2 is going to be negative 390. 2 SO2 is going to be, well, 2 times negative 290. And then I'm going to subtract the enthalpy to make the reactants. In other words, subtract 110. In other words, plus negative 110, which is exactly what we did there. So you can do it that way if you like as well. Both of them seem to work. Number 6 is a tricky one because you can't find the CF bond directly, but what you can find is this. If you have CF4, that's just 4 CF bonds, and if you decompose it into carbon plus 4 F atoms, not F2s, not 2 F2s, just 4 F atoms, then that will be 4 times the delta H for the CF bond. And so once you find that, then you can just divide by 4 to get the answer. It's a bit of a tricky question. So that's what we're going to try and get to. Let's see if we can make it work. Okay, there's equation 1 rewritten in reverse. The other thing that I haven't really mentioned is that I'm looking for the bond enthalpy is always calculated in the gaseous phase. In other words, the amount of energy required to break 1 mole of a bond in its gaseous phase. So I want to make sure that I have gaseous carbon, but you'll notice that here I have solid carbon. So I want to make sure that I use this reaction to give me gaseous carbon on the right-hand side. And then all I need to do is break apart those 2 F2 molecules using equation 2. And that's going to be 316 because I'm doubling this whole reaction here. And then just cross out whatever is common on both sides, like the solid carbon and the 2F2 gas, and I get exactly what I'm looking for, CF4 gas producing carbon gas plus 4 Fs, and that totals 1711 kilojoules, but that's for 4 CF bonds. I just want it for 1, so it's just 1711 divided by 4, and that's your answer. Okay, tricky question, but there it is done for you. Okay, we are all done. Your test is coming up November 6th. That's a week from yesterday. Cool. See you on Friday, folks. Or maybe I've already seen, you know what I mean. I'll see you soon.